Definition. The perimeter of a polygon is the sum of the lengths of all sides of the polygon. Table 8.1 summarizes perimeter formulas for types of triangles. Table 8.1 Perimeter of a triangle. Scalene triangle. Perimeter equals A plus B plus C. Isosceles triangle. Perimeter equals B plus 2S. Equilateral triangle. Perimeter equals 3S. Table 8.2 summarizes formulas for the perimeters of selected types of quadrilaterals. Table 8.2 Perimeter of a quadrilateral. Quadrilateral. Perimeter equals A plus B plus C plus D. Rectangle. Perimeter equals 2B plus 2H, or perimeter equals 2 times the quantity B plus H. Square or rhombus. Perimeter equals 4S. Parallelogram. Perimeter equals 2B plus 2S, or perimeter equals 2 times the quantity B plus S. However, it is more important to understand the concept of perimeter than to memorize formulas. Find the perimeter of triangle ABC shown in figure 8.17 if A. Length AB equals 5 inches, length AC equals 6 inches, and length BC equals 7 inches. Solution. A. Perimeter of ABC equals length AB plus length AC plus length BC equal to 5 plus 6 plus 7 equals 18 inches. Note, perimeter is a linear measure of the sum of the lengths of each exterior edge of the figure. Find the perimeter of triangle ABC shown in figure 8.17 if B. Altitude length AD equals 8 centimeters, length BC equals 6 centimeters, and segment AB is congruent to segment AC. Solution. With segment AB congruent to segment AC, triangle ABC is isosceles. Then segment AD is the perpendicular bisector of segment BC. If length BC equals 6, it follows that length DC equals 3. Using the Pythagorean theorem, we have length AD squared plus length DC squared equals length AC squared. 8 squared plus 3 squared equals length AC squared. 64 plus 9 equals length AC squared, or length AC equals the square root of 73. Now, perimeter of ABC equals 6 plus the square root of 73 plus the square root of 73. Perimeter ABC equals 6 plus 2 square roots of 73, which is approximately equal to 23.09 centimeters. If the lengths of the sides of a triangle are known, the formula generally used to calculate the area is Heron's formula. One of the numbers found in this formula is the semi-perimeter of a triangle, which is defined as 1/2 of the perimeter. For the triangle that has sides of lengths A, B, and C, the semi-perimeter is S equals 1/2 the sum of A plus B plus C. Theorem 8.2.1 Heron's formula. If the three sides of a triangle have lengths A, B, and C, then the area, capital A, of the triangle is given by area equals the square root of S times the quantity S minus A times the quantity S minus B times the quantity S minus C, where the semi-perimeter of the triangle is S equals 1/2 the sum of A plus B plus C. Find the area of a triangle which has sides of lengths 4, 13, and 15. See figure 8.19. Solution. If we designate the sides as A equal to 4, B equal to 13, and C equal to 15, the semi-perimeter of the triangle is given by S equals 1/2 the sum of 4 plus 13 plus 15. 1/2 times 32. S equals 16. With S equal to 16, Heron's formula, capital A equals the square root of S times the quantity S minus A times the quantity S minus B times the quantity S minus C, becomes area equals the square root of 16 times the quantity 16 minus 4 times the quantity 16 minus 13 times the quantity 16 minus 15. Area is equal to the square root of 16 times 12 times 3 times 1. Area equals the square root of 576. Area equals 24 units squared. When the lengths of the sides of a quadrilateral are known, we can apply Heron's formula to find the area if the length of a diagonal is also known. In quadrilateral ABCD in figure 8.20, Heron's formula can be used to show that the area of triangle ABD is 60 and the area of triangle BCD is 84. Thus, the area of quadrilateral ABCD is 144 units squared. Theorem 8.2.2, Brahmagupta's formula. For a cyclic quadrilateral with sides of lengths A, B, C, and D, the area is given by capital A equals the square root of the quantity S minus A times the quantity S minus B times the quantity S minus C times the quantity S minus D, where S equals 1/2 the sum of A plus B plus C plus D. Recall that the two parallel sides of a trapezoid are its bases. The altitude is any line segment that is drawn perpendicular from one base to the other. In figure 8.21, segment AB and segment DC are bases, and segment AE is an altitude for the trapezoid. We use the more common formula for the area of a triangle, namely area equals 1/2 BH, to develop our remaining theorems. In theorem 8.2.3, B sub 1 and B sub 2 represent the lengths of the bases of the trapezoid. Theorem 8.2.3, the area, capital A, of a trapezoid whose bases have lengths B sub 1 and B sub 2, and whose altitude has length h, is given by capital A equals 1/2 h times the quantity B sub 1 plus B sub 2. Given that segment RS is parallel to segment VT, find the area of the trapezoid in figure 8.23. Note that length RS equals 5, length TV equals 13, and length RW equals 6. Solution. Let length RS equal 5 equal base 1, and length TV equal 13 equal base 2. Also, length RW equals h equals 6. Now, area equals 1/2 h times the quantity base 1 plus base 2 becomes area equals 1/2 times 6 times the quantity 5 plus 13. Area equals 1/2 times 6 times 18. Area equals 3 times 18. Area equals 54 units squared. Theorem 8.2.4. The area of any quadrilateral with perpendicular diagonals of lengths D sub 1 and D sub 2 is given by capital A equals 1/2 D sub 1 times D sub 2. Recall that a rhombus is a parallelogram with two congruent adjacent sides. In turn, we proved that all four sides were congruent. Because the diagonals of a rhombus are perpendicular, we have the following corollary of theorem 8.2.4. See figure 8.25. Corollary 8.2.5. The area, capital A, of a rhombus whose diagonals have lengths D sub 1 and D sub 2 is given by capital A equals 1/2 D sub 1 times D sub 2. Corollary 8.2.5 and corollary 8.2.6 are immediate consequences of theorem 8.2.4. Example 5 illustrates corollary 8.2.5. Find the area of the rhombus MNPQ in figure 8.26 if length MP equals 12 and length NQ equals 16. Solution. By corollary 8.2.5, area of MNPQ equals 1/2 diagonal 1 times diagonal 2 equals 1/2 times 12 times 16. Area of MNPQ equals 96 units squared. In problems involving the rhombus, we often utilize the fact that its diagonals are perpendicular. If the lengths of a side and the length of either diagonal are known, the length of the other diagonal can be found by applying the Pythagorean theorem. For a kite, one diagonal is the perpendicular bisector of the other. See Figure 8.27. Corollary 8.2.6. The area, capital A, of a kite whose diagonals have lengths d sub 1 and d sub 2 is given by capital A equals 1/2 d sub 1 d sub 2. Find the length of segment RT in Figure 8.28 if the area of the kite RSTV is 360 inches squared and length SV equals 30 inches. Solution. Area equals 1/2 diagonal 1 times diagonal 2 becomes 360 equals 1/2 times 30 times d, in which d is the length of the remaining diagonal segment RT. Then 360 equals 15d, which means that d equals 24. Then length of RT equals 24 inches. The following theorem compares the areas of similar triangles. In Figure 8.29, we refer to the areas of the similar triangles as a sub 1 and a sub 2. The triangle with area capital A sub 1 has sides of lengths a sub 1, b sub 1, and c sub 1, and the triangle with area capital A sub 2 has sides of lengths a sub 2, b sub 2, and c sub 2. Where a sub 1 corresponds to a sub 2, b sub 1 to b sub 2, and c sub 1 to c sub 2, Theorem 8.2.7 implies that capital A sub 1 divided by capital A sub 2 equals the quantity a sub 1 divided by a sub 2 squared, or capital A sub 1 divided by capital A sub 2 equals b sub 1 divided by b sub 2, the quantity squared, or capital A sub 1 divided by capital A sub 2 equals c sub 1 divided by c sub 2, the quantity squared. Theorem 8.2.7. The ratio of the areas of two similar triangles equals the square of the ratio of the lengths of any two corresponding sides. That is, area sub 1 divided by area sub 2 equals the quantity a sub 1 divided by a sub 2 squared. Use the ratio a sub 1 divided by a sub 2 to compare the areas of a. Two similar triangles in which the sides of the first triangle are half as long as the sides of the second triangle. Solution. S sub 1 equals 1/2 S sub 2. So, S sub 1 divided by S sub 2 equals 1/2. See Figure 8.30. Now, area sub 1 divided by area sub 2 equals S sub 1 divided by S sub 2, the quantity squared, becomes area sub 1 divided by area sub 2 equals 1/2 squared, which equals 1/4. That is, the area of the first triangle is 1/4 the area of the second triangle. Use the ratio a sub 1 divided by a sub 2 to compare the areas of b. Two squares in which each side of the first square is 3 times as long as each side of the second square. Solution. S sub 1 equals 3 S sub 2. So, S sub 1 divided by S sub 2 equals 3. See Figure 8.31. Area 1 divided by area 2 equals S sub 1 divided by S sub 2, the quantity squared, so that area sub 1 divided by area sub 2 equals 3 squared, or area sub 1 divided by area sub 2 equals 9. That is, the area of the first square is 9 times the area of the second square.